Hello again. So I am excited for today's lecture because we are going to start the idea of derivatives. And that's one of the biggest things that you'll learn in calculus. We're only going to slightly touch on the actual definition of a derivative in this lecture. We'll get on that right at the very end. But we're going to talk mostly about the concept leading up to derivatives, and that's going to be rate of change. So let's jump right in. And I want to start off with a definition of the average rate of change of a function. And what might help is, rather than thinking of this as a function, think of you driving a car. And if you're driving on the highway and you're going certain speeds and your speed changes, but you could think of the average speed over the course of your trip. Maybe you're on the highway for part of it, maybe you're on back roads for some of it, maybe you're stopped for some of it, at a rest stop or something like that. And you have varying speeds over the entire trip, but you do have one average speed. You could think that maybe you stopped and you sped up and you slowed down. But if somebody else just drove one particular speed and without stopping and they just drove that speed the entire way, they would get there in the same amount of time as you. Maybe because you drove faster for part of it, but you drove slower for other parts, and it would just kind of average out so that you had an average speed. Definitionally, with a function, we can say that if I'm talking about two different x values, a and b, so if I'm looking at a function in between x equals a and x equals b, let's go ahead and draw a function right here. So if I've got my function right there, and I'm going to look at x equals a and x equals b, I'm looking at those 2 points, I can talk about the average rate of change. And as you can see, it's actually just a slope formula. It's just the values. Let me do a different color here. So I've got my f of a and I've got my f of b. And the formula here, this average rate of change formula that I have written there, f of b minus f of a over b minus a, that's actually just our slope. Let's do a different color. That doesn't really stand out. So that purple line right there, that's just our slope, and that's that average rate of change. So you're going to take the starting point and the ending point, and you're just going to do a rise over run with them. Write that in, rise over run. Great. So we've got that idea of average rate of change. Let's look at an example here. Let's say you're driving and your time is in hours and your distance is in miles. So when you start off, time is 0. The trip begins. You haven't traveled anything at all. After 1 hour, you've traveled 15 miles. Great. At that point, your average rate of change, think about it, the average speed that you've driven is 15 miles per hour, because over 1 hour you've driven 15 miles. Now, it doesn't matter if you drove really fast for part of it and really slow for the rest. Just over the course of that entire trip, you've averaged 15 miles per hour. And so we could write that up here. We could say, average is 15 miles per hour at this point. And then what we could do now is we could look, okay, after 2 hours, you've driven 26 miles. So in this stretch, you've driven 11 more miles, which is a little bit slower than you were just going. Well, what we've got here is, on average, you've covered 26 miles in 2 hours. So your average speed would be 13 miles per 1 hour. So 13 miles an hour, for 2 hours, you'd go 26 miles. And so your average speed is slowing down a little bit. And that's okay. That's just, again, maybe you drove really fast for part of it. Maybe you drove really slow for part of it. But on average, you're at 13 miles an hour. And then I can keep going. You can see 12 miles per hour on average here, and then 10 miles per hour on average here. And we're kind of just looking at this, and we're just, we're saying, hey, if I cover you know, for over 4 hours, if I cover 40 miles, I'm going 10 miles an hour. And you can kind of just think about that. But really, what I'm doing on every single one of these calculations is I'm doing 15 minus 0 over 1 minus 0. I'm doing that f of b minus f of a over b minus a. Here I'm doing 26 minus 0 over 2 minus 0. Here I'm doing 36 minus 0 over 3 minus 0. So I'm just always taking my f of b, in this case right here, 40, minus my f of a, which is my starting point, 0. And then I'm doing 4, which is my b, that time, over 0, that starting time. And you're getting these blue answers, 15, 13, 12, and 10, appropriately. Now, I've been calculating these average rate of changes starting from the start point, going up until 1 hour, then 2 hours, then 3 hours, then 4 hours. But what if I wanted to talk about the average rate of change from the first to the third hour? Well, what I could do is I could do exactly, again, this formula. And I kind of laugh because it's basically the same thing, just some different numbers. We could do f of b minus f of a over b minus a. And if we're just going to look at the average rate of change between hours 1 and 3, what I'm going to do is I'm going to take my 36, because that's the distance at 3 hours. I'm going to subtract off the distance that I was at 1 hour, and then I'm going to do 3 hours minus the 1 hour. And here I'm going to get 21 over 2, and that's going to give me 10.5 miles per hour. And that's my average speed just for the portion of the trip between hours 1 and 3. I could do this for any other portion. I could go between 1 and 4. I could go between 2 and 4. I could go between 3 and 4. You could do any section of the trip that you wanted to, but you always have some average speed that you've gone, this average rate of change. And so that's kind of it on that sort of algebraic sense of average rate of change. You're really just thinking about it as speed, basically. Obviously, the units might not be miles and hours in terms of time and distance. You could have just a regular old function, but generally it helps to think about rate of change as speed. So let's go ahead and let's take a look at this function here. And what I'm going to do is I'm going to take the point x equals 4, and I'm going to take the point at x equals 7 to start off with. But really, I'm going to just focus on that x equals 4 for now. And if we do this, I'm going to look at that point at x equals 4, and I'm going to look at that point at x equals 7. Okay, and I'm going to draw a line between those. And when I draw that line, that's me drawing a line with a slope that is the average rate of change, right? Remember, f of b minus f of a over b minus a. I mean, this is akin to y2 minus y1 over x2 minus x1. It's basically rise over run, right? And so if I just take these 2 points in the blue right there, then what you've got there is exactly just this average rate of change, right? And so this red line is going to talk about average rate of change. And what you could do is you could figure out the slope of that line, and that would tell you that average rate of change. Let's go ahead and write that down. So m equals average, I'll just say ROC, rate of change. So the slope of that line is the value of average rate of change. Now, let's watch what happens as I bring this this point here at 7. So remember, like I was saying, I was carrying about 4 and 7. Now what I'm going to do is I'm going to take this point here and I'm going to bring it in a little bit. And you'll notice, so I originally had this line up here. So that past slide, it looked like this. I can try and make that line up appropriately. There you go. So on the last slide, it was the purple line. On this slide, I've now got the red line because what I've done is I've taken this X coordinate here, maybe a little past 7, and I've shifted it just over a little bit. And once I shift it over, I then draw that connecting line from 4 to that new X value that I'm looking at. And you can see that line, the red line, that slope is a little bit shallower than it was for the purple. And so what I've got here is I also have an average rate of change, but it's an average rate of change from the time period between 4 and, I don't know, maybe we call that 6 3/4 or something like that, just between those greens. Before, I had the average rate of change from 4 to, let's say, 7, right? Maybe a little more than 7. And so what I'm doing is I'm shrinking that interval of where I'm looking at for my average rate of change. What I'm going to do next on this next slide right here is I'm going to, let me actually copy this right here. So this is the same slide as what I had, just not marked up. I'm gonna change the slide, and you're gonna see that line is going to get even a little more shallower. And so what I'm doing, I'm still keeping, here, I'll do that again so you guys can see that. Just going back and forth. That 4 is not changing. I'm still looking at X equals 4, but my X value on the right is getting a little bit closer and closer to 4. So I'm still looking here, but now this X value here, let's draw that a little straighter, maybe like 6.5 or something like that. And so my average rate of change is a little bit less. That slope is a little bit smaller. It's a little bit shallower of a slope. That average rate of change is less. And I'm going to keep doing this. You're going to watch that red line, and watch that red line continue to change right here. Oh, for some reason, it's not wanting to change. There we go. Sorry, the recording's being a little slow. So you're watching that red line change here. It's getting shallower and shallower. And you'll notice what's starting to happen is, this is maybe a better one to look at. I'm getting closer and closer to 4, and this is probably at 5 right there. As this rightmost point is getting closer and closer to 4, this line, it keeps getting shallower and shallower, but eventually it kind of just touches that curve at one particular point. And because it's touching at one particular point right there, how do we do this f of b minus f of a? I mean, here, what if I zoomed in here and we tried to look at this? So if I try to calculate f of b minus f of a, well, where the heck are the 2 points of intersection, right? I mean, I've got a point right there, but that's kind of the only spot that it touches at. Before, what I had, I had a line here, and I had 2 different points that it touched at. But as that line gets shallower and shallower and shallower, these 2 points that it's touching at, they start to just be one particular point right there. And that's a problem, because if we try and do f of b minus f of a over b minus a, and let's just say that we're looking at x equals 4 here, what this is going to end up being, like we said, it's the same point. There's only one point. Well, f of 4 minus f of 4, those are just the same thing, right? So that's 0 on the top, and 4 minus 4 is 0. So I just get 0 over 0. And what have we seen with limits? 0 over 0 is bad. That's an indeterminate form. And so what we're seeing here is that as I take this red line, and so I'm going the opposite way now. I'm making that red line get a little steeper and steeper. As I bring this rightmost point over here, as I bring that in closer and closer to x equals 4, this average rate of change gets shallower and shallower up until the average rate of change ends up just being 0 over 0, which is an indeterminate form, and we don't like that because we want a value for this average rate of change. So we gotta ask ourselves, what the heck do we do next? And let me go to the next slide here. Let's go ahead and look at what we've just done here. So let's say that I've got x equals a, and therefore I have an f of a that corresponds with that point right there. And then let's say that I go a small distance h right there. So I'm gonna add h to that original x equals a that I meant. That means that my new x coordinate is just a plus h. Therefore, that gives me a y coordinate that corresponds there, and that's going to be f of a plus h. So if I'm doing my instantaneous, or if I'm doing my average rate of change formula here, what I've got is I've got my b and my a, right? I've got one point here and another point there. And so what I'm going to do is I'm just going to do what we've been doing. I'm going to do my rise over run between those two orange points. And if I do that, I have exactly this formula right here. I've got f of a plus h, that's this y value right here, minus f of a, that's this y value right here, divided by the x's in difference, a plus h right there, and a. And so this formula right here, that is my average rate of change. Let me write that down. Let's say, we'll go average rate of change. That's that average rate of change right there. Let's put an equal sign. And so that's my formula for average rate of change. And what we just talked about when I went through all of those slides where I made this red line shallower, all of this right here, I'm doing this in opposite. I'm making it steeper now as I flip through these. But as this red line gets shallower, what I'm doing is I'm actually taking that rightmost point and I'm bringing it over to that x equals 4. And what that's doing here on this picture is I'm shrinking the value of h. I'm bringing this a plus h, this rightmost point, closer and closer to a. And that's shrinking the value of this h here. So what I just said verbally, we can actually turn that into a limit. I'll say it again as I flip the page. I'm going to shrink the value of h all the way down to 0. Let me rephrase that. I'm going to take h and I'm going to let h approach 0. When I use that word approach, that should be screaming limit to you guys. So what I'm doing here, what I did on those slides before is I took this red line and I made it shallower, and I took this rightmost point and I just sort of brought it closer and closer and closer and closer and closer until it hit A, is that I'm taking that value of h right here and I am letting it approach 0. And that's exactly this limit here that we're seeing. That's the whole idea of a limit, is me taking the limit as h approaches 0 of this guy right here. And what did we say happens when I bring this rightmost point closer to A? What happens as I shrink h to 0? Well, what happens is I end up with this picture right here. I end up with just that line with just one point right there, and I end up with that indeterminate form. And that sort of connects the two things. We've got a limit right here. And apparently, if you evaluate this limit, if you let h approach 0, you end up with 0 over 0 for your answer. You end up with just 0 over 0. And that's bad, right? That's an indeterminate form. But what I'm really trying to make clear here is that these steps here that I did, where I took this average rate of change line, I took this point here, and I let it get closer and closer to 4, what I'm doing is a limit. And when I do that limit, I end up in this scenario right here, where I just have the red line touching the black function at one particular point. And because it's touching at one particular point, we give it a name. We call this the instantaneous rate of change. And what this is it's the slope of this red line. And now, obviously, we don't have a way of calculating f of b minus f of a over b minus a in this case. We get 0 over 0, so we don't know what to do. But that doesn't mean that this red line does not have a slope. It has a slope. It's just that that slope, we don't know how to calculate it yet. And that's because we have 0 over 0 here. So luckily, we've done some limit magic before, and sorry, I went a little far. We've done some limit magic before, and we've said, hey, if I have a limit here and I get 0 over 0, we've seen multiple ways that I can edit that limit algebraically to turn it into a limit that gives me an answer. One way was factoring and then some cancellation. One way was that conjugate multiplication. And then one way was common denominator. We had that issue where the numerator had two fractions added or subtracted from each other. And so we had to find a common denominator. So we saw these multiple ways. That was on that limit magic lecture. And so really what I want to make clear is we run into this issue of this 0 over 0 with this limit here, but we know how to sort of get ourselves out of that pickle with these methods here. So let's go ahead. I've talked about instantaneous rate of change here, and that idea of instantaneous rate of change just being the slope at this one particular point right there. This red highlighted line that I'm drawing right now, that has a slope to it. This line only touches the function at one particular point, and so that's what we call instantaneous rate of change. Now, I'm going to come right back here to this slide in a little bit. What we've got here, when I've said instantaneous rate of change, another thing that you could use to describe that red line is a tangent line. And so I'll redraw this, what we had. We had this graph here. We had that function that goes like this. And at this point here, we had an instantaneous rate of change right there. We had that line that only touches at one particular point. And that's actually the definition of a tangent line. If I give you a function and you can draw a line here that only touches it at that one point, we call that a tangent line. And like we saw, that tangent line has a slope. And the way that we figure out what that slope is we do this limit as h approaches 0. I take this value of h here and I shrink it to 0, and that gives me this straight line, and that tells me what the slope is. So what I'm doing is I'm taking this average rate of change formula, and I'm basically saying, hey, as h gets smaller and smaller, this no longer really becomes an average between two different points here. It just becomes an instantaneous rate of change at one particular point. And so that's sort of the thing to ingrain in your heads, is that an average rate of, the limit of the average rate of change becomes instantaneous rate of change, all right? So one other thing I want to mention here, notice that in this denominator, the a and the h, a plus h minus a, that'll cancel nicely, so we just have an h down there. I'm going to go ahead and copy this over onto this other slide. So we've got this definition of a tangent line. Let's go ahead and compare that to this right here. So I've used a different letter. I've used the letter C instead of A. That's what a lot of books will do for some unknown reason. But the format is basically the same here. What I've got, you'll notice this numerator is just f of a plus h minus f of a. I got the same format here, just with C instead of A. And then down here, I've got a plus h minus a. So these a's are going to cancel. And I'm left with just an h. And that h is right there. So this big box formula here, that's the same thing as what we saw previously. And so we have this formula. We say, okay, if I were to take an average rate of change between two particular points, and I then take one of those points and I drop it down, I shrink that value of h, right, down to 0, I end up with just this instantaneous rate of change. And we call this line a tangent line. It has a slope. That slope is given by this formula. And that's kind of big. That's this big formula here. Now, we can evaluate this formula like we saw. We're going to get 0 over 0 if we do a direct substitution. But luckily, we've talked already about ways that you can edit a limit to not get 0 over 0, right? To change the function around a little bit so that you get a value as opposed to 0 over 0. And we'll do examples of that next time. But let's go ahead. What I want to do is, so I've said this before. I'm going to say it one more time. The slope of this red tangent line over here is given by this limit, okay? So we actually have a name for that, and that's called the derivative. If I have a function and I want to talk about the derivative of that function at a particular point, that's just the slope of that tangent line, which we just saw on the last slide. That was limit as h approaches 0 of f of c plus h minus f of c all over, you could say c plus h minus c, but that just simplifies to just h. So I'll just write an h here. This right here is the derivative, which is the slope of the tangent line. Those are the same exact thing. When if I say derivative and then separately I say slope of the tangent line, those are the exact same thing. I'll go ahead and write that out. Derivative equals slope of tangent line. I mean the same exact thing. Because I'm taking that h, I'm shrinking that distance down. That makes me just have that tangent line that just touches at one particular point right there. And that line has a slope. That slope is given by this, and we call it the derivative. That's just a nice name for it. And there we go. So in recap, just to kind of take everything that we've talked about and put it in, put everything right next to each other. We've got our average rate of change, right? And our average rate of change is given by that f of b minus f of a all over b minus a. If we take that average rate of change and we take those 2 points, the a and the b, and we shrink those so that they're the same point, that gives us a line, a tangent line, that only touches the function at one point. And we call that an instantaneous rate of change as opposed to average rate of change. So if you just have 1 point on that function that you're considering, instead of having 2 points, like instead of having an a and a b, you just have 1 point. That point has an instantaneous rate of change associated with it. Then that instantaneous rate of change, obviously on your graph you have a tangent line, and that tangent line has a slope that we can calculate with that formula limit as as h approaches 0 of f of c plus h minus f of c all over h. And that value right there, that limit, if you evaluate that, that's called the derivative, and that gives you the slope of the tangent line at that particular point. And that's actually going to be it on the lecture, but I do want to go back and just reference one thing. So we've got this formula here, boxed right here on the slide. This is what I've said this over and over. This is the formula for the slope of the tangent line. It is a formula for the derivative. Alternatively, you are allowed to use this formula. This is the same exact thing. Instead of dealing with this idea of an h, I'm just dealing with points A and B, and I'm taking B and I'm letting it approach A, and that's what I'm doing with this limit. You get the same exact thing. This is fine. We're going to do several algebraic examples of this as well, so don't worry too much if you're looking at this and you're like, what? Like, that's fine. Just remember, we've got our formula for the derivative, which is the same thing as the slope of the tangent line, and that's the slope of this red line here that I've got. So that's it for rate of change and the intro to derivatives. We'll see you next time to talk more about derivatives.